previous breakdown, we looked at how greedy algorithms operate. They blindly commit to the best immediate local option. That saves processing time, but because they never look ahead, they risk missing the optimal global solution. But dynamic programming takes the exact opposite approach. When it breaks a problem down into smaller pieces and finds an answer, it permanently stores that result. The next time it encounters that exact same smaller problem, it skips the math and pulls the answer directly from memory. This chart maps out where this strategy fits into the wider landscape of algorithmic design. Looking at the top right, dynamic programming sits right between the fast local choices of greedy algorithms and the exhaustive search patterns of backtracking. The gap between a quick, risky guess and a provably perfect strategy comes down entirely to how an algorithm manages its memory. To see why this memory allocation matters, we have to look back to 1950, inside the Rand Corporation during the early days of the Cold War. Mathematician Richard Bellman was tasked with solving multi-stage decision processes. These were complex optimization problems that required finding perfect schedules over time, where choices made today restricted the choices available tomorrow. His primary obstacle was the U.S. Secretary of Defense. The secretary openly despised the word research and was actively hostile toward funding pure mathematics, making Bellman's highly theoretical work a prime target for budget cuts. Bellman needed a way to hide his math in plain sight. He chose to name his work Dynamic Programming. The phrase sounded impressive. It focused on planning, and, as Bellman noted, it was impossible for politicians to use the word dynamic in a pejorative sense. Behind that political smokescreen lies a highly efficient mechanical truth. Dynamic programming is simply the ultimate mathematical tool for eliminating redundant work. The mechanism operates on a strict rule: solve a subproblem exactly once and remember the answer. Despite the name, the programming part of dynamic programming has nothing to do with writing software code. In this specific mathematical context, it refers to filling out a tabular schedule or a matrix of answers. While a greedy algorithm makes a fast choice at the top of a decision tree and never looks back, dynamic programming builds its answers from the bottom up. It exhaustively reconsiders past choices, but it does so cheaply by constantly referencing its stored cache of results. Because it explores the entire subproblem space without wasting time on redundant calculations, it is guaranteed to return a provably optimal answer. This diagram outlines the calculation of a Fibonacci sequence, mapping out the waste caused by overlapping subproblems. On the left side, the naive recursive approach finds the fifth number by calculating the fourth and the third, but finding the fourth also requires calculating the third. The system repeats the exact same work over and over. On the right side, we apply memoization. By storing the answer to the third Fibonacci number the first time it gets solved, the algorithm can pull it directly from memory the second time. The branching tree collapses into a straight line of cache hits. This dynamic programming table illustrates a more complex challenge, the 0-1 knapsack problem. The goal is to maximize the value of distinct items you can fit into a limited capacity, in this case, 5. The algorithm builds the answer from the bottom up, filling the grid row by row. To fill the final bottom right cell, it simply compares two known values from earlier in the table, the value of skipping the final item versus the value of taking it. It reads the optimal answer directly from its own ledger. Abstract, complex decision trees are flattened into straight rows and columns. Time previously spent recalculating is completely eliminated. The impact on processing time is staggering. For both Fibonacci and the knapsack problem, this logic takes an algorithm that would require exponential time and compresses it down to linear time. In logistics, solving the traveling salesperson problem using brute force math means checking every single delivery route permutation. That requires factorial time, a scale that breaks modern computers with just a few dozen stops. Dynamic programming handles that same data with a vastly reduced computational load. In Python, you can often execute this memory storage with almost no structural changes to your code. Adding the @LRU cache decorator above a recursive function automatically instructs the language to store and reuse the return values. A single line of memory allocation serves as the ultimate weapon against computational bloat. This graphic shows the two specific conditions a problem must pass to use this method. First, it needs an optimal substructure, meaning the optimal whole is built from optimal pieces. Second, it needs overlapping subproblems, meaning the same calculations actually repeat. When those two rules apply, this logic powers heavy global infrastructure. It runs airline routing, optimizes delivery fleets, and processes millions of data points for genetic sequence alignment. But it does have strict limits. If subproblems are totally independent and don't overlap, you need a divide and conquer strategy. And if your data sets are so massive that a dynamic programming table exhausts your physical memory, you have to abandon perfect optimization entirely and rely on heuristic approximations. The mechanics, use cases, and constraints of these design strategies are detailed in 50 algorithms every programmer should know, which provided the foundation and diagrams for this breakdown. Dynamic programming finds the optimal path by remembering what works, but sometimes finding an answer requires remembering what fails. In our next video, we cover backtracking, an algorithm that explores an entire data structure, retreating the exact moment a path hits a dead end.